everybody, welcome to 1.1. We're going to start off with a definition, and our definition is called recursion. You may or may not have seen this before. So recursion is a process in which each step of a pattern is dependent on the step or steps that come before it. It is often easy to define a pattern recursively, and a recursive definition reveals a lot about the properties of the pattern. Alright, so we kind of need to know, like, what's the next step? You need to know what the previous step was in order to get to the next step, and you need to know that one to get to the next step. So I'm going to give you an example of what this really looks like. Alright, so we look at this example A. A square table seats 4 people. 2 square tables pushed together seat 6 people. 3 tables pushed together seat 8 people. How many people can sit at 10 tables arranged in a straight line? How many tables are needed to seat 32 people? And it says, write a recursive definition to find the number of people who can sit at any linear arrangement of square tables. So we can start off just by saying, here's 1, 2, 3, 4, right? And we have the fourth one here. So there's 1. And then if we just say, okay, let's just get another table and we'll put it right here, right? So now we have the 1 that's out here plus 1, 2, right? And then we'll add another table. I'm going to put it here, and then we're saying there's still the 1 out here, and then we add 1, 2. And then we get another table, and we keep on going, right? So we can keep on doing this, and you kind of say, like, how many are we adding every time? I'm not putting the 1 out there because I don't want to keep on erasing it. But every time we add 1 table, how many chairs are really adding to it? We are adding 1, 2. Right, so if we were to make a little table, to make the, get it? We're making a little table. Do you get it? Table. There we go. So what we could do is we could say table over here. And that would be the table number, and this would be the number of chairs. So when we had 1, 2, 3, 4, and then we want to say how many can sit at 10 tables arranged in a straight line? How many tables are needed to seat 32 people? So we can go 5, 6, 7, 8, 9, 10, and we can do dot, 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 and then we want to get to 32. Okay, so 1 table had 4, 2 tables had 6, 3 tables had 8, right? 1, 2, 3, 4. We'd have 2, 4, 6, 8, and then 10, and then 5 is 12. We have 14, 16, 18, 20, 22 is at 10 tables put together. So we have 10 tables put together, there's 22 people, and then it'd be 24 is 11, here I'm going to use a different color, 26 is 12, 28 is 13, 30 is 14, and 32 would be 15. So if we needed 15 or 32 people all in a straight line, we need 15 tables pushed together that are like this style table. Alright, so there we go. So we want to try and write a recursive definition. And we don't have enough time, room to write it here, so what we're going to do is we're going to just write it up here. And let's get this color. So what we could do for our recursive definition. Our recursive definition, we'd say number of people at 1 table is 4, and we'd say the number of people at the nth table. And when I say nth table, we say that because we don't know which table we're at. So we're going to say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We don't know which table we're at, so where we're stopping at. So we're going to say the nth table. What we need to do is we need to know the number of people at the n-1 table. Okay, so actually I'm going to write that whole thing. I'm going to say people at the n-1 table. So we're going to say people at the there we go, n-1 table. And then when we added another table, how many people did we add? If we go back, how many people did we add? We added 2 every time we added a table. So we'd say number of people at the previous table plus 2. So this n-1 right here Really what we're saying is that's like saying the previous table in this case, all right? So at the nth table, n minus 1, that's really just the previous table, okay? And that would be a recursive definition. So let's talk about a sequence. A sequence is an ordered list of numbers. The table and graph in example A represents a sequence. We didn't really have a graph, but this is just our sequence. 4, 6, 8, 10, 12, 14, 16, 18. That's a sequence. Okay, 4, 6, 8, 10, 12. Each number in the sequence is called a term, and the first term, u sub 1, pronounced, again, u sub 1, is 4. The second term, u sub 2, is 6, and the third term is u sub 3, which is 8, and so on. And the nth term, u sub n, is called the general term of the sequence. General because we don't have an actual number attached to it. A recursive formula, the formula that defines a sequence, must specify one or more starting terms, and recursive rule that defines the nth term in relation to a previous term, or terms. Sometimes you might need more than one. So if we do the recursive formula for the table problem in example A, we'd say u sub 1 equals, so when we had 1, that 1 down here, in this case, could represent the table number, all right? And then what it equals, we have 4, that's the number of people, all right? So this would be, okay, so u sub 1, 1 meaning the table number, is 4, that's the number of people. So that's part of the recursive formula. The other part is going to be the u sub n, the general term, is going to equal, so we're saying the nth table is going to be the number of people who are sitting at u sub n minus 1, the previous one, plus we add 2 chairs or 2 people every time we add a table. Right, so the whole thing, so when we write this recursive formula, we need both parts. So we have this part and we have this part. We need both. Kind of like in a line, you need to know where do you start and how much do you change by. We need to know where do you start, what's the first table going to be. Because if we don't know where we start, this is kind of useless, because if we don't know, take the previous one, add 2, add 2, add 2, add 2. At some point you have to say, I need to start somewhere. I can't just keep on adding 2 every time. So we're going to say u sub 1 equals 4 and u sub n equals u sub n minus 1 plus 2. We need both of those for our recursive formula for example A. Alright, we need both of them. Alright, so here's example B. A concert hall has 59 seats in row 1, 63 in row 2, 67 seats in row 3, and so on. The concert hall has 35 rows of seats. Write a recursive formula to find the number of seats in each row. How many seats are in row 4? Which row has 95 seats? Alright, so what we can do is we could just make a quick table, and we could just kind of check to see how this is going to work out, to see if we can find out what number do we start at. So we say the top can be row, the bottom can be seats. So we say row 1, row 2, row 3, row 4, row 5, row 6, row 7, row 8. Let's just go that far. So we know row 1 is 59, then 63. Row 3 has 67, and it says and so on. So what we have to try and do is let's figure out, is there some sort of common difference? If I say 63 minus 59, I get 4. 67 minus 64, I get 4 again. So it seems like if I add 4 to 67, I'll get the next one. So 64 plus 67 plus 4 gives me 71, and then 75, and then 79, and then 83, and then 87. Alright, so we're adding 4 every time. That seems like that makes sense. So since we're adding 4 every single time, right, that makes it a little bit easier to figure out this recursive sequence. So where do we start when we're writing a recursive sequence? U sub 1, in this case, because we're starting with row 1, right, U sub 1 equals 59. So we need to know, where do you start? Alright, and then how much are we changing? That's kind of the next one. We're taking u sub n, our general term, and we're going to say that's u sub n minus 1. And what are we adding every single time? We're adding 4. Alright, so this is where we start, this is what we add, and this whole thing would be our recursive sequence. So after that, could we figure out which row How many seats are in row 4? Well, we know that one, 75. And can you figure out which row has 95 seats? I'll give you a second just to figure that out right now. Okay, so in example B, the terms of the sequence are related by a common difference. Common meaning the same, difference meaning subtraction. And if there's a common difference every single time, if we just add 4, add 4, add 4, add 4 every single time, then we call this an arithmetic sequence. Alright, arithmetic meaning like adding or subtracting. Okay, hence why it's arithmetic. Okay, there are going to be different types of sequences that we talk about later, but here is a formal definition of arithmetic sequences. An arithmetic sequence is a sequence in which each term is equal to the previous term plus a constant. This constant is called the common difference. If the letter D is the common difference, then the recursive rule for the sequence has the form u sub n equals u sub n minus 1 plus d. Now what are they missing? They're missing the u sub 1, but we're going to get that anyway. Once you get some information about the problem, you're going to be able to say u sub 1 or u sub 0, u sub 3, u sub 5. We have to start with something, but they're talking about just the common difference. So the key to identifying an arithmetic sequence is recognizing the the common difference. We want to know what is that number that you add or subtract from the previous term to get to the next term. If you are given a few terms and need to write a recursive formula, first try subtracting the consecutive terms. If u sub n minus u sub n minus 1 is constant for each pair of terms, then you know your recursive rule must be a rule for arithmetic sequence. So for example, if I just subtract 63 minus 54 and all of these and I get a 4 every single time, then I know that it is an arithmetic sequence. Okay, there you go. Good luck.